All right, how we doing, everybody? Doing good. All right. So how was the spring break? How'd you guys do? Pretty good. Not too bad. Everyone got some sleep, or not enough sleep, or play games. I don't know. Listen to that new BTS album that just came out. Anyways, let me see. Minimize this. Let's see where we are with the semester. So that's Dr. Morris. What do you guys think? He's cool. Wonder what happened to his like hot picture. You guys seen his other picture? He looked like got the bow tie and everything. Let me see. Brendan Morris. Yeah. Where is he? Yeah, look at that. Yeah. I missed that one. It's hot. Anyways. 360D. Doom. What did we do the last time? I don't remember. Spring break Laplace transforms. Okay, how are we doing with Laplace transforms? How's Dr. Morris doing with it? Not too bad. Are you guys understanding what's going on? I'll give you guys a quick little breakdown of what the Laplace rule or transform is and why you're doing it, why you're learning it. All right, is that good? What else did you guys learn? Actually, what did you guys do? Do I click on this link? No, that's Panopto. How do I see the PowerPoint? Just this one right here, right? What is this? PFE, partial fraction expansion. Ooh, I highly recommend everyone study this, okay? I highly recommend everyone study this. Yeah. You're going to be seeing this in your exam. I'm recording this right now because I think a few of these problems are on your exam. Yeah, this one right here. This one. Yeah, okay. Well, replace this J omega with S. Yeah, I like this one. Okay. And it has discrete time. Perfect. Oh, okay. Who wants to do this for homework? Where is it? He doesn't give you. Okay, yeah, do this example too. He doesn't give you a linear constant coefficient difference equation. He doesn't give you one. But if you can memorize this right here, that's a bad one. He doesn't give you an example. But yeah, study. Yeah, heavy side cover-ups. Yeah, study this one, okay? This is very important for your exam, okay? I promise you that. Anyway, let me go to the PW or OW. What does OW stand for? Yeah, I don't know either. We'll just talk about this. I don't. Let me see. Visualizer. Boom. Cool. Now let me just point the camera down there. So Laplace transforms. Okay, so what is a Laplace transform? Why do we use it? It's for frequencies. Did he say that word in class? Frequencies, vibrations, decays, exponentials. So you'll realize every signal that you'll ever encounter, including my voice, it's going to be a function of, let's just say, it's going to be a function of time, right? Function of time, correct? Everyone's used to this, right? It's going to have some type of amplitude, right? A, right? Is that correct? And it's going to change over time, and I don't know what it is, but let's just put an exponential, okay? I'm just going to throw e to the, let's do minus, do I want to do a or alpha? Let's do alpha, alpha t. Is that good, right? Good signal. It's got a magnitude, and it's got some type of decay or whatever this thing is here, amp, right? And then some, I don't know, we call it an attenuation, right? Is that cool with everybody? You guys know why I call it attenuation? Let me show you guys a scary problem, or I don't know, maybe not too scary. What if I show you a signal like this? Let me see. Let me think of a signal. I'm going to do this. Here's time. I'm going to call this one I T. Okay? Let me grab another color, because this is very important, and a lot of students don't understand this until they graduate, and they're like, oh, so that's what David was talking about. And I'm going to do this time right here, right? It's just, can you see that color? Is that okay? Let's use an orange, okay? I'm going to spike this up here, right? You see that right there? And then it just decays like this, right? Is that cool? What do you think I'm trying to do right here? See if anyone remembers this circuit. Guys, remember that? The current going through a capacitor, if I were to go from, I don't know, oh yeah, I'm going to give you guys some PTSD, plus, minus. It's bad, plus and minus. Step from 0 to 1, right? Right? What's the instantaneous current, right? When I go from 0 to 1, it's going to be like instantaneous current, but the voltage is, well, it doesn't want to change, right? Because it needs a charge, right? So if I were to do IT like this, you get a spike of current, right? Actually, let's talk about this. I need to know your guys' 320 fundamentals. If the initial voltage right here, right, is Vt at t is equal to 0 is 0, right? Right? And I switch this on, right? So now VDD, there's 1 volt right here. 1 volt right there, right? What's the current? The instantaneous current. If this was, I don't know, 1K. I is equal to V over R, right? If I have 1K, right, and 1 volt, and this is right here is 0 volts, what's the current? 1 milliamp, right? Is that good? Everyone understanding this? What about the voltage? I'm going to draw the voltage, okay? Because this is very fundamental. Baker teaches it like this, Dr. Baker. If an electronics person teaching signals and systems would teach it like this, so I'm teaching you this, okay? If I were to do V of t, right, what's the voltage at 0, right? It's 0, right? So if I were to draw like this, let me use a green marker, okay? Okay? What's going to happen with the voltage? It's going to charge, right? Right? Is that cool? What's the settling voltage right here? When this is fully charged, and this is 1 volt for all time. 1 volt. Is that hard? Not too hard, right? And then look, this looks like a step response, right? Step, boom, and what does it hold at? 1 volt, right? Does that make sense? And then this right here is also a step response, right? Right? The step response. Okay. You know what I'm talking about when I say step response, right? I turn the system on, right? What's the step response of the voltage? It looks like this, boom, right? What's the step response of the current? Boom, and it decays. Are you seeing the connections now? All right, I'm just trying to get you guys engaged with what's going on. And oh yeah, and then what about the slopes, or what is this right there? You can calculate that with like the RC time constant, right? Easy. Anyways, would you like to do this via the hard way using integrals and convolution, stuff like that? No, it gets a little painful, right? But that's where Laplace, this funny guy, he's like, you know what? There's an easier way to do circuits, and that's where he comes up with this little guy. Let me show you. Don't worry, I'm just trying to get you all warmed up to this, okay? X of t is equal to a e to the minus alpha t u of t, okay? I'm just going to do it like that, okay? Where every signal is going to have an amplitude and some type of decay, okay? Is that cool with everybody? And then you can transform this. Did he show you how to transform it from going from this to Laplace, right? Where the Laplace transform of x of t, right, is equal to x of s, right? Did he go over this? How do we go from the time domain to the s domain? Well, first we got to look at the entire signal, correct? The entire signal, right? So when I'm looking at the entire signal, I'm thinking integral, right? Integration, s is equal to minus, or not s, t. The entire time, right? plus infinity, right? The entire time of the signal, x of t, right? But then I have to multiply it by some type like orthogonal or basis like function, right? So the engineer said, let's kick an Euler, or not Euler's equation, but like an exponential, and an exponential pops out. So you do the following: e to the minus s t and then dt, right? Is that correct? Am I getting this right? Whew, I remember. Anyways. So basically what we're trying to do is, let's look at a signal, right? Okay? I'm going to look at like this time right here, okay? I'm just going to circle a time. Let's use a black marker, okay? And I'm going to investigate this area right here, okay? Right? That part of x of t, right? So for a certain time, right? For this signal right here, I'm just multiplying whatever this frequency and this time is, right? To just analyze it for its frequency. S. What is S equal to? Some whatever this thing plus j omega, right? Is that correct? Right? Remember that from class? Some attenuation coefficient. What do you call it? Yeah, this is actually the better way of writing the attenuation coefficient. This is, let me see. I'm going to skip some steps. Attenuation, right? And then this right here is just the cycles. Right? Frequency. Not too hard, right? That's S. It's got a frequency component. Is that good with everybody? Everyone's following me? Okay? So I'm just going to look at this signal for a little bit of time. Look at the change of the time with this e to the st, right? And then all of a sudden, magical things happen, okay? To the point where you get this beautiful table that I'll show you right here. Let me see. S domain. So let me see. This is the omega terms, and this right here is S is equal to that. S is equal to j omega right there. Is that cool with everybody? Right? And remember how we have this, let me just say, like, was it this guy right here, right? We have this kind of funny signal. It's a right-sided signal, right? It's real, it's going forward in time, and it's stable, right? So if I were to say, hey, this signal right here, I'm just going to do an example. Let me just do it right here. I of t is equal to, I don't know, 1 milliamp e to the minus t over tau right there, right? Where, what's it called? Let me think. Alpha is equal to 1 over tau, right? Is that cool? Is that making sense with everybody? Wait, minus or plus? Okay, this is where I get confused. No, this is correct. Minus tau. Anyways, bear with me. So I wanted to make sure this is stable. I'm going to do something like this. I'm just going to do this right here, okay? Alpha, right? That's my alpha term. Is that correct with everybody? Did he teach you about the region of convergence, right? ROC. What does ROC also stand for? Subaru joke? No one wants to hear it? Republic of? And you can finish that sentence for me. Anyways, did he also teach you about this imaginary axis right here? Right? And a right-sided function has to be stable and include the imaginary axis. Like that, right there. Boom. That's your region of convergence right here, ROC. And this right here is your pole, okay? And it includes this entire axis, okay? So that's how you know your thing works. Did he talk to you about how to draw on the Laplace transform or how to generate any signal from the Laplace transform? Did he teach you that? You want me to show you? If I were to do the following, okay? Let's do Laplace transform. That's a funny L. S. You guys know how to read this? Right? And tell me about the frequencies. Okay, if I were to tell you right here, right, 1, okay? What does this signal look like right here? You guys know what it looks like? It's going to look like this. Okay, this is time, right? It's going to look like this. I don't know, some value, A, or something like that. DC, right? It's a DC signal, right? What about right here? Well, we're going to have some frequency, right? It's going to start spinning around in a circle, correct? Okay? And if this is T, right? Without DC or something like that, but I'm just going to wiggle it like this. Like that, right? It's got a frequency component. Is that correct? Right? Well, technically not like this. I'm just looking at the real components, right? We get a sine wave. Is that cool? But it's a positive frequency. So right here, going this direction, you get positive j omega, right? But going down this way, you get minus j omega. Is that correct? So what is this one going to look like? It's going to have a negative frequency component. So it's just going to wiggle like the other way around. Let me see. Like this. Yeah, that's a bad drawing. But you see what I mean? And then if you add this right here and this right here, right? P1 and P2, right? Because complex conjugates, you get the real signal back. Does that make sense with everybody? What about here? If I were to draw an X right here, right? I'm going to call this one R1 or something like that. What is this going to look like? It's going to look like, actually, before I go there, let me talk about this one right here. If I were to draw an X right there, right? R2 or something like that. What's this one going to look like? Remember the current going through the capacitor? It's going to shoot up like this, right? Is that cool? So what about this one? It's not including this imaginary axis, right? It's going to be unstable, correct? So what's it going to look like? It's just going to go just up. Is that cool? Exponential growth. That makes sense with everybody? How about if I do an X right here? I'm going to do, I don't know, P3 and P4, right? What is that going to look like? It's just going to be a decay, what do you call it? It's going to be a signal that decays. Let me see, because this one decays, it's just going to be like this. Like that, right? And then this right here, too, is going to be like, well, you can't see the negative component, but I'll show you, like something like this. All right? Complex conjugates, you add them together, right? And you get the real signal back. All right? That's a big rule. You can't have a complex pole without its conjugate, okay? So make sure, don't forget that, okay? This guy has a partner with this guy's got another partner, okay? If you have a single pole that's just lying around like right here, right, it doesn't exist. You have to have its partner, okay? Make sense? Anyways, who's ready for me to do the assignment? Then you guys can go home. Fundamentals. So this is the assignment that I saw on the website. Oh, hey, how you doing? Morris. Yeah, I think a few EE girls switched into EE, and they're like, "Oh, we're gonna see Dr. Morris," and I'm like, "I think he looks like this," and he doesn't look like it. And they're like, "Well, I think he's still cool. I like him." Cut your hair, Dr. Morris, please. I miss you. Brendan Morris? Really?
Yeah, that's political science.
They will teach it.
Huh? Interesting. I didn't know that. Wait, what? This guy? Hey, look at this guy. Hey, he was wearing the same shirt today. Anyways, let's get back to work. So going to the website, okay? He's got Comp 5, Comp 6, and Comp 7, okay? Is that good with everybody? 3 more assignments and we're done? Click on Comp 5. This shouldn't be too bad of an assignment, okay? It's a walkthrough. This is Dr. Stuber's old assignment. I wish I could have given him my real edited assignment. Personally, I'm burnt out. I got other labs to fix on, okay? So you guys are doing soldering in my labs. You guys are doing PCB design. We're doing a lot of cool stuff in the labs. But we got to go back to fundamentals of signals and systems. It all builds out of there, okay? Anyways, so it's the same assignment from Dr. Stuber's old lab, so be my guest. You know a YouTube channel to look up. Z-plane, not too bad. What's this right here? Transfer function, right? Of the impulse response transfer function, right? System, H of S, right? And then how do you split this and find the poles? Or actually, wait. If you wanted to model this, you can model this using this right here, right? Z-plane. Anyone want me to see me do that? Show you, okay? Because everyone's scared and like saying, I just want to go home, man. I don't blame you too. So let's do this. EE 360D. What lecture am I on? Lecture 6. What do you call it? Poles. So if I were to do A is equal to 1, 3, 2, right? And then I do B is equal to 1, 7, 12, right? And if I do Z-plane, let me do this, figure, system, or name, system plane, question mark, okay, subplot 2, 1, 2 or 1, there we go, Z-plane BA, see if that runs, Control Enter. Hey, look at that. Can you see that? Yeah, my computer screen sucks. So let me just do the following. Can I, let me see. Let's ask, what do you call it? Z-plane MATLAB. Because I wonder if we can make this prettier, because I can't see it from my end. It's I need it to be a little thick. Let me see. Axis. What other parameters can I change? It's not telling me if I can change colors. Let me see if I can show you something. Help. No, wait. Oh, wait. I have a better one. If I go here, let's see if I can change attributes. Insert. No worries. I'm wasting too much time. But do you see right here? I have a pole right here. I have a pole right here. I have a 0, 0. Right? And here's my imaginary axis. Is this a stable system? Yeah? Cool? And then let me just call this, can I title it? My stable system. Ooh, cool. Nice. So now, I think Dr. Stuber says, can we do it a second way? I want to build this system, but like this. I want to build it based on poles, okay? So what if I do the following? AP is equal to -1, -2, and BP. You guys know why I'm calling AP and BP? Pole. A pole. I'm just going to type it. Okay, pole. Where's my poles at? It's at -3 and -4. Okay. What am I going to do here? Subplot 2, 1, 2. Z-plane A pole. A pole. B pole. Hold up. Sorry, I messed this up. It's the B's and the A's. There we go. And then let me just title this. Title, my stable system, but I invented the pole to be stable. There we go. What do you mean no? Oh. Any questions? All right. So that's how you know you can build your own system. You can build systems in two ways. You can get the whole polynomial, or you can just attack for the poles and the zeros. All right. So keep that in mind. How about the roots or the poly? Okay. Poly, roots, yada, yada, yada. You can read that. Ooh, this is important. I want to run this system, okay? Let me see if I have to do anything here. I want to run the system. Residue, boom, boom, boom. Because I think this is going to generate an error, so I'm going to fix it for you right now. Okay, let's fix this right now so I can make your homework assignment easy. Kicking boxes. Okay, so I'm going to create clear vars, okay? Just work with a clean slate. 1, 3, okay? B, or wait, this is B. I'm going to call it numerator. Denominator, okay? Is that cool with everybody? I'm going to space it out like this because I like it when things are clean. 1, 7, and 12. Okay, is that cool with everybody? I'm going to do a thing called RPK. What does that stand for? No one plays Call of Duty here? I'm playing, it's okay. Residue B, or numerator. No. Yeah, numerator, denominator. There we go. Is that cool with everybody? It's asking for the numerator first and then the denominator first, or next, okay? B-A, num, then. Is that good? Any questions about that? So now I'm going to kick this box. Oh, give it a time. T is equal to, from 0 to, 5. But I'm going to add a thing. Call it my, I don't know. I don't know. What's the word for fine tuning, or I don't know, tune or fine number. I'm just gonna create a number, 0.025. Okay. Why did I do that? Because you can change the time, right? Increments or something like that. Don't believe me? See that right there? 5 seconds right here, 4.975 seconds, 4.95. You see that? That's what I'm doing right there. What if I want to do it in increments of 0.1? Is that cool? Easy? H, our impulse response, right? R dot times, or dot, what do they call it? Parentheses? I forget what it is. Quotation mark, times exponential of cron pt, and it ran. Cool. So let me do this. Figure name box kicked. Okay. Subplot. Let me see if I can do something funny. Input X, right? What did I do to this box? I kicked it, right? At times equal to 0, right? Impulse response. Is that correct? Times 0. Actually, no, I can't show you that. Bless you. Yeah, I can't show you that. No, we can't. I can't model that for you. It's okay. Plot. You're going to be using the plot function for now. T and H. Woo! Is that cool with everybody? What if I did this? Or actually worse, let me do this. What is that? Actually, let me just show you. Line width 3. Does this look pretty? No? Why? Because it's an analog system, but we're doing it in 1 second steps. It's not good, right? So that's why we had this fine number right here. I don't know, 0.1. Looks a lot prettier, right? Okay, any question? Actually, it could be a lot prettier. I can see it staggering. A lot cleaner, right? Cool? Hey, what if I do the following? Because this is a good lesson, okay? Kicking our intro box. So I'm going to do the following. I'm going to do R1, P1, K1, okay? Is equal to, what do you call it? Residue. Remember these numbers right here? Right? Remember this? I'm going to kick this box right here. B pole, A pole, right? Remember that? I just want to kick it, right? It'd be fun to know what it looks like, correct? So I'm going to do H1 or something like that is equal to R1 dot boom exponential cron P and T. And then let me just copy paste. You guys like copy pasting? Boom. First box kicked. Then H1. Whoa. That looks pretty cool. Right? Actually, why am I getting 2 lines? Investigating. R1, 2, P1, 2, K1. Okay. Check. Dr. Stuber, help me. So we have a K value that needs to be used. So let me see, because there's a ghost number here, and you guys don't know this, but I do. Let me see if it shows you in this assignment. There it is. No, that's not a time representation. Do you know what cron stands for? Kronecker delta. I'm kicking a box. Kronecker, just kick. Okay. Let me just see it. MATLAB cron. Kronecker tensor function product. Anyways, let me just look at something. Residue, MATLAB residue. Because I forgot how to use the K's. Residue. How do I get back to time? Honestly, you don't need to know this, but it's good to know. Actually, it's very important to know. Because this R is the residue, okay? Every pole is going to have a residue. Let me go back to this graph, okay? Let me show you what I was trying to talk about. Remember this graph right here, right? So you're going to see poles, okay? And these poles are going to have, some poles are a lot bigger or smaller than other poles, okay? Some infinities are bigger than other infinities. Does that make sense? So this pole right here, I don't know, it's going to have a residue of, I don't know, was it 1 milliamp? Question mark, right? So every pole right here, so this right here is going to have res 3, and this one is going to be, I don't know, this right here, res, I don't know, 1 or something like that. Every pole has a residue. Okay? Does that make sense? RP, right? And then K is just the gain. Okay? I haven't looked into that deeply, so that's a good example that we looked into. Anyway, because I did this and I'm getting 2 lines, and that shouldn't have happened, but now I'm interested. I'm intrigued. Anyways, I'll look into that. Let's go to your assignment. Example 1. Let's see, right here. Oh, yeah. And then, let's see. To generate y of s, the numerator polynomials of h of s and h of s and x of s can be multiplied together. And you can use the convolution function. I'm going to say this again. Conv. Don't forget it, okay? Someone's going to forget it. Using the conv function. Honestly, you can choose this assignment in like 5 minutes. Or actually, not really 5 minutes, but like 10. I'll give it 20, personally. Determine the system function transfer functions h of s. How do we do that? You guys remember? Let me just pull this out, okay? We're going to do your homework. You guys like it when I do your homework? Already too busy with the labs? Me too. Wait, this is page 2. No, this is page 3, sorry. 3, 2, 1. Okay. Anyways, let's get back to work. So what is our transfer function? Anyone bother if I do this? 2a, right? Plus a2 plus omega naught 2 is equal to x prime plus ax. Is that good with everybody? Open this. Boom. Cool. Do you guys remember, has he shown you how to actually generate or get the transfer function from this? You guys remember that? Where, if you have, what's his name? Yeah, I'm gonna skip some steps. Where y of t converts to y of s, right? Remember that? Right? And then y prime of t converts to s y of s, right? Remember that? And then what if it's the unilateral Laplace transform? Or t is equal to 0 minus, I think, right? Or Laplace transform, right? Did he teach you that? No, is he not? Or were initial conditions? Yeah, so don't forget this one. But for now, we're just dealing with this because I don't care about the initial conditions right now, okay? We're just building a system. We don't know what it does. What about this one? Right? We're going to have s squared, right? Y of s, right? And then for the unilateral Laplace transform, we're going to have minus, was it s, what do you call it? Let me remember this. S y prime t is equal to minus 0. Yeah, this minus, I think this is what it was. I might be wrong. Is that correct? Does that look familiar to what you guys did in the notes? Yes or no? You're shaking your head. Is this familiar? Okay, perfect. The point is, don't worry about this. He might throw this on. I know Dr. Stieber throws this on the exam. I don't know what Dr. Morris does. I'll ask him, okay? But anyways, this is the more important thing, okay? Comp 5, okay? Memorize this. Promise me, okay? Same thing with x. It's the same thing. Easy, okay? I'm going to change all this into y primes and s's, okay? Is that cool? So what I do with y prime, double prime, right? Should I include the y there or should I skip it? Okay, I'll put it in there. Plus 2a s y of s, right? Plus a squared plus omega naught squared y of s, right? Is that cool? What is this all equal to? Rewriting this again. Y of s, right? S squared plus 2as plus a squared plus omega naught squared, right? Easy. Can I skip a step for this guy? Or not? I don't know. Someone's going to get angry at me. S x of s, right? Plus a x of s, right? Which is equal to s plus a, right? Oh, sorry. Someone yell at me when that happens, okay? Anyways, this is page 4. So much talking today. Nice. Who's ready for the grand finale? The answer to your actual problem 1. You guys like that I'm doing your homework? No, man, you're cheating us. Nah, it's okay. Before I even write your answer, what is h of s? So what should I do with this guy? Divide it under here, right? And then divide the x of s over here. Let's see. Determine the system's transfer function h of s. Boom. Are you gonna make Joanna happy? Yeah, she's smiling. Look at her. She's gonna grade and she'll be like, they're all getting A's. Okay? Make her happy, all right? She's the one grading your papers, okay? Calculate h of s for this. Okay? So we're gonna do some things, but personally, I'm gonna give you guys the bread and butter of the answer. Okay. Let me see, because I developed something for you. Because you're gonna have to create your own S-plane. Does that make sense? You're gonna go from -10 to 10, right? Okay. Let me just show you a piece of paper. You're gonna have to give me. You're gonna draw a mesh of this right here. Okay. Does that make sense? So you're going to go from -10 to 10, right? But also imaginary, right? So you're going to make a whole matrix. Does that make sense? So if I said, okay, if I'm going from -1, 0, 1, right? That's 3 points, correct? But I also have to do it for here, here, here for the imaginary number right here, right? And also for the bottom, right? 1, 2, 3, 4, 5, 6, 7, 8, 9 points, correct? Right? I'm gonna expand that out, okay? So it goes from -10 to 10. Give me a 10 square. Cool? So let me see. Let's code this. Close all. Okay. So let's create our real axis. I don't know. Let me see. S, real val, or I don't know. R. What should I call this one? Was it what's that symbol? I forget what it was. Sigma? Sigma, was that the sigma? Oh, the funny shape. Do you guys know what I'm talking about? Let me see. This guy right here. Right? What is this? Is that sigma? Yeah, sigma, okay. Anyone bother if I call it sigma right here? From -10 to 10, right? And then I'm going to call this one omega for the imaginary axis, right? Okay. But what am I going to do with the precision? I'm going to call it ds. I'm going to call it 0.1. Okay. ds. Okay. Is that cool? So now I need to create the square, but personally I don't remember it. So let me just see if I can generate this from a different, let me see, LaPlaceTransformPlotter.com. I love Dr. Morris. He let me reuse my assignments. See DS? See small increments? There we go. You're going to have to use this, okay? There's 2 ways of doing it. You can do it the easy way or the hard way, but personally, we're going to do it the easy way, mesh grid. Because we have an x-axis, right? And we have to copy it up and down, correct? And we have a y-axis, right? But I have to copy it left and right, right? So mesh grid just does it all like that. Cool? So I'm going to do this. Copy, paste, you guys can have it. And then I'm going to do sigma and omega. Cool? And I'm going to get real and imaginary values from that, right? Is that correct? Yes? And then I'm going to add them all so it can be one big S domain. Okay? S real plus S imaginary. What did I do right here? I added the J right there. Do you want that there or do you want that here? I don't know. Give or take. Explain it to me, okay? Your pick. Cool? Anyways, what did I do? Let me go back to my solution guide. I'm playing now. It's not a solution guide. It's a tool. The size of our play field. Ah, okay. Oh, this is easy. Man, you guys are getting cheated. So you guys remember pre-allocating memory, right? Right? We're pre-allocating memory. Does that ring a bell? We got to do the same thing for MATLAB or for our plane, okay? We're going to create a clean slate of numbers. Everything's going to be defaulted to 0. Is that good with everybody? So what did I do right here? The size of the play field, right? Right? Just create a whole 0. Is that cool with everybody? Where did I get this? Let me see. Give me a second. There it is. Was this assignment hard? Or not because no one started it? Okay. Hey, look at this. This looks like the answer to the second problem. Or the third problem. Is that cool with everybody? Oh, wrong one. So then, is that all I do? Let me see. Figure 1, because I'm lazy. Okay, why did I say proving my sanity? Let's see. Boom, boom, boom. Is that cool with everybody? Okay, let's just go over it one step by step because I'm seeing some blank faces, okay? What is this? What is this line right here? Figure 1, right? Easy. No one's lost me. Mesh. That's a function, right? Let me go back here. Mesh. Where's the mesh function? Mesh C function, right? Cool. Is everyone following me? Or is everyone passing out? What is this right here? The real value, right? Imaginary. 20 log 10 of the absolute value, right? Cool. What is this right here? Labels. Run it. What the heck? My 0. Oh, you know why I failed that? Because I got to do the following. Wait. Hold up, come on. There we go. My zeros, okay? My poles. Is everyone understanding what I'm doing right there, right? Let me just do this. How do you want to calculate? Where is our answer that I calculated? That we calculated. That, right? What's our zeros? This right here, right? What's our poles? Right? How do we type that? You guys remember how we did it? Hold up. Right? Something like this, right? We just need to ignore this part, just copy this. Boom. Or not this. Boom. This, remember this, right? Easy. So let me do this. Not my zeros. I'm going to call this one my numerator. My num. My den. Is that cool with everybody? My num is going to be equal to 1 and a, right? Or is that what I'm calling it? I'm going to call it. Do I have a somewhere else? I don't know. I'm going to call it. Yeah, let's just keep it calling it a. Because you know why I'm hesitating calling it a? It's because what did we call this right here? A. I don't like reusing. I don't like. You see, I started getting a little scared about like you doing that. So I'm going to call it attenuation or something like that. Or I don't know, alpha. 1 or something like that. Does makes sense? My den, right? How do I do my denominator? 1, 2, dot times alpha 1 dot times. Wait, no, that's it. Okay. And what about here? Let me see. Alpha 1 dot squared plus omega. I'm not going to call it omega. I'm going to call it, actually, okay, omega. Wait, no, I can't call it omega either because I called it right here. I'm going to call it W0. Okay? Is that cool with everybody? Everyone understanding my coding? Not trying to destroy my previous variables? Alpha 1. What's A1 or alpha 1? What did he give you? 1.5, right? And he gave you 7 over here. 1.5 and W0 is equal to 7. Is that cool with everybody? Ready for me to do your homework? Yes. Roll them. Clean. You guys like that? Pretty cool, huh? If I were to rotate it like this, right? You see the imaginary axis right there? And the real axis? This is 0 right here, right? Is this a stable system? No? Yes? Is it stable? It's on this side, right? On the left side, right? The poles are on the left side of the axis, right? So it's stable, right? Cool? And then that's pretty much it. Yeah, that's problem 1. And then frequency response. You guys want me to go over it? Yes, no, or do you want me to wait till next week? Next week, you guys want to go home? Yeah, I'm ready to go home too. But anyways, please understand the Laplace transform is pretty chill. This assignment shouldn't be too hard because guess what he did? Yes. Let me click here. This is Dr. Morris's page, right? 2026, correct? I'm going to click here, and no one complained to me. Right? Right? No one complained to me, okay? He took out 2 pages for you, so 2 pages less of work. All right? Have a good day.